Hello everyone, I'm Mehdi. Welcome to this channel. I'm happy to explore the world of imperfections or crystalline defect with you today. We are diving into the topic of imperfections in solids, which is all about the different kinds of flaws and defects that show up in materials and why they matter. Alright, let's get into how solidification works, specifically in metals. When we are casting a metal, we start with it in a fully molten liquid state. As it cools down, the material begins to change from liquid to solid in a two-step process, which shapes the final structure of the metal. Nucleation, this is where it all starts. Tiny solid particles, called nuclei, begin to form within the molten liquid. Think of these as tiny starting points that set the stage for solid growth. Nucleation usually happens first in cooler spots within the liquid, where atoms move slower and are more likely to arrange themselves in a stable pattern. The higher the cooling rate, the more of these nuclei will form, which can lead to a finer grain structure. Number two, crystal growth. Now these nuclei start expanding, with each nucleus growing into a larger crystal. As cooling continues, these crystals spread out, extending their structure in all directions. This is why we see in the second photo. So, as each crystal expands, it eventually meets neighboring crystals, which brings us to the third photo, where all of these growing crystals meet and form boundaries. At this stage, we now have a fully solid structure made of grains, each separated by grain boundaries. Now let's look at different grain structures that form as metal solidifies. When a metal cools and hardens, the grains can take on different shapes based on how fast or slow the cooling happens. Equiaxed grains. These grains are roughly the same size in all directions, often forming near the mold walls where the cooling is fastest. That rapid cooling at the edges encourages small, uniformly shaped grains. The next one, columnar grains. Deeper inside the metal, where cooling happens more slowly, grains have more time to grow longer in one direction, creating column-like structures that align with the direction of heat flow. To get more of these smaller equiaxed grains, we sometimes add grain refiners. These help produce a finer, more uniform structure throughout, which generally gives the metal better mechanical properties like improved strength and toughness. By controlling cooling rates and using grain refiners, we can significantly improve the final quality and performance of metal products. Now, let's talk about grains and grain boundaries in detail. So, when we look at a solid material, it is not just made of one giant crystal. It is composed of many smaller crystals called grains. So, how about the grain boundaries? These are the regions where two grains meet. Here, you can find some misalignment in crystal structure. This thing means there is a bit of atomic disorder at these boundaries. This atomic disorder is actually significant. It leads to high atomic mobility. At grain boundaries, atoms can move around more easily compared to inside the grains. This can affect how the material responds to stress or heat. And high chemical reactivity. The disorder at the grain boundaries can make these areas more reactive chemically. So, this is why grain boundaries can be important sites for processes like corrosion. You might see different types of grain boundaries based on the angle of the misalignment. For example, A high-angle grain boundary shows a larger misalignment, while a small-angle grain boundary has a smaller misalignment. These differences can influence how the material behaves under various conditions, like when it is being deformed or heated. Well, let's focus on imperfections in solids. First off, it's important to note that there is no such thing as a perfect crystal. Every crystal has some kind of imperfection or defect. These imperfections are not just rare, they are present in every single crystalline material. Now, why does this matter? Well, the properties of materials like their strength, conductivity, and reactivity can be greatly affected by these defects. For example, a small change in the arrangement of atoms can change how a material behaves under stress or how it conducts electricity. So, what exactly are these crystalline defects? We call them crystalline defects, which refer to any irregularity in the lattice structure. These defects can have dimensions that are about the size of an atom. Think about that. Something so small can have such a big impact on how a material works. In the next slides, we will explore the different types of imperfections that exist in solids. These include point defects, line defects, and surface defects. Each type has its own characteristics and influences the material in unique ways. Now, let's get into the type of imperfections we can find in solids. We typically categorize these imperfections based on their dimensions. First up, we have point defects, which are zero-dimensional. These are tiny irregularities in the crystal structure that can significantly affect the material's properties. The three main types of point defects are vacancies. This happens when an atom is missing from its regular lattice site. Imagine a seat at a concert being empty. That's what a vacancy is like in a crystal. It creates a disruption in the arrangement and can affect how material behaves, like making it less dense or altering its electrical properties. Next one, interstitial atoms. These defects happen when an extra atom is squeezed into the spaces between the normal atoms in the lattice. Think of it as an uninvited guest fitting into a crowded room. This can change how atoms interact, which can enhance or reduce a material's strength. The next, substitutional impurity atoms. This is when one atom in the crystal lattice is replaced by a different type of atom. For example, if you take some copper atoms and replace them with zinc atoms, you create a new material that has different properties than pure copper. This type of defect is common in alloys. Next, we have linear defects, which are one-dimensional. The main type of these are dislocations. They are irregularities along a line in the crystal structure. Dislocations play a crucial role in how metals deform. When stress is applied, these dislocations move, allowing the material to change shape without breaking. This movement makes metals more ductile and easier to work with. Finally, we have interfacial defects, which are two-dimensional. The primary example is grain boundaries. They are the interfaces where different grains or crystals meet in a polycrystalline material. Grain boundaries can affect various properties like strength and corrosion resistance. The arrangement of atoms at these boundaries is often different from the atoms in the grain themselves, which can lead to variations in how material behave under different conditions. Well, now let's talk about point defects in metals, which are the simplest form of imperfections but can have a significant impact on materials properties. First, we have vacancies. They are simply vacant atomic sites in the crystal lattice. When an atom is missing from its normal position, it creates a vacancy. Imagine a crowded classroom where one chair is empty. That empty chair is like a vacancy in the atomic structure. This missing atom can cause distortions in the surrounding planes. These distortions can affect how the material behaves, specifically in terms of diffusion, which is how atoms move through the crystal lattice. The presence of vacancies can also influence the mechanical properties such as hardness and ductility. Now let's move on to self-interstitials. They happen when host atoms are positioned in the interstitial spaces or gaps between the regular atomic sites in the lattice. Think of it like someone trying to squeeze into a tight spot in a packed room. This creates additional distortion in the atomic planes, as the presence of these extra atoms in the interstitial sites alters the arrangement and spacing of surrounding atoms. Self-interstitials can also impact the material's mechanical properties, often making the material stronger, but also more brittle. In the images we see here, you can notice how vacancies create a disruption in the orderly arrangement of atoms, leading to a distortion of the planes around them. Similarly, self-interstitial also cause distortion as these extra atoms push against the surrounding structure. When we talk about vacancies in metals, it is essential to understand that the equilibrium concentration of these vacancies changes with temperature. The formula we use is NV over N equals exponential of negative QV over KT. N sub V is the number of vacancies we have. N represents the total number of lattice sites in the material. QV is the activation energy needed for the formation of vacancies. And K is the Boltzmann constant, which has a value of 1.38 times 10 to the negative 23 joule per atom Kelvin. So, T is the absolute temperature measured in Kelvin. It's interesting to note that each lattice site has the potential to become a vacancy. So, the higher the temperature, the more vacancies we can expect to form because the atoms have more energy and can jump into the vacancy sites more easily. Well, to find the activation energy for vacancy formation, or QV, we can determine it through experimental methods. The process involves measuring how the concentration of vacancies changes with temperature. We can plot the data in two ways. Initial plot starts with a graph of NV over N versus temperature T. So here N stands for the total defect concentration. In this plot, you will notice that the relationship shows an exponential dependence, meaning as temperature increases, the ratio of vacancies to total sites increases rapidly. If we replot data, so to make it easier to analyze, we can take the natural logarithm of the initial plot. This gives us a new graph with ln nv over n plotted against 1 over t. So, in this transform plot, the slope of the line will give us the value of negative qv over k, where k is the Boltzmann constant. This method allows us to calculate the activation energy by rearranging the slope. All right, let's calculate the equilibrium number of vacancies. Now we move to the second step where now let's look how we can observe changes in equilibrium vacancy concentration, particularly in a material like NiAl. When we look at the 110 surface of NiAl through an electron microscope, we can see fascinating changes as we increase the temperature. As the temperature rises, we notice that the surface islands of atoms start to grow. So, what is happening here? It all comes down to the increase in equilibrium vacancy concentration. As we hit the material, more vacancies are created within the bulk of the crystal. These new vacancies then start to diffuse toward the surface of the crystal. This diffusion is important because these vacancies can contribute to the growth of the surface islands. As they reach the surface, they essentially become part of these islands, which are clusters of atoms. The process maintains equilibrium between the vacancy concentration in the bulk and the surface. If we visualize this, you can think of the surface islands as dynamically adjusting to keep that balance. If more vacancies appear in the bulk due to the increased temperature, the islands grow larger. Conversely, if vacancies are reduced, the islands might shrink. This dynamic behavior shows how temperature and vacancy concentration are interconnected, influencing the material's microstructure significantly. Now let's talk about the impact of impurities in metals. When we introduce impurity atoms like B into a solid made up of Haas atoms A, there are generally two main outcomes we can observe. First, we can form a solid solution of B in A. It means that the B atoms get randomly distributed throughout the A atoms, creating a homogeneous mixture. In this case, the B atoms can occupy the lattice sites of A. Depending on their size, they can either fit into the regular lattice structure as substitutional atoms like copper atoms in nickel, or they can fit into the spaces between atoms as interstitial atoms, such as carbon atoms in iron. This kind of random distribution can significantly alter the properties of the host metal, such as its strength. So, the second outcome happens when we add a higher concentration of the impurity atoms. In this case, we still have a solid solution of B in A, but we also start to see the formation of particles of a new phase. These new particles have a different composition and often a different crystal structure compared to the original host metal. This can lead to a range of effects on the mechanical properties of the material, such as an increased hardness or changes in brittleness depending on the nature of the new phase. So, the presence of impurities is crucial in materials as it affects not only the structure but also the overall properties of materials. Well, I'm gonna continue discussing the conditions that need to be met for forming substitutional solid solutions as defined by Hume-Rothery rules. First, the atomic radius difference between the host metal A and the impurity metal B should be less than 15%. This similarity in size helps the impurity atoms fit into the crystal lattice without causing significant distortion. If the size difference is too great, the structure may become unstable, preventing a solid solution from forming. Next, the two metals should be close to each other in the periodic table. This often means they have similar electronegativities, which helps promote the mixing of the two metals. When the electronegativities are similar, the bonding characteristics are more compatible, allowing for better solubility. The third condition is that both metals must share the same crystal structure. For example, if metal A has a face center cubic FCC structure, then metal B should ideally also have an FCC structure. This alignment in crystal structure allows for easier integration of the impurity atoms into the host lattice. Finally, we consider the valences of the metals. Generally, a metal is more likely to dissolve another metal than has a great valence than one with a lower valence. So, this is because metals with higher valences can better accommodate the additional bonding interactions that arise in the solid solutions. By following these guidelines, we can better predict whether two metals will form a substitutional solid solution and how their properties might change as a result. So let's apply the Hume-Rodary rules to a practical example, determining whether more aluminum or silver would dissolve in zinc. First, we look at the atomic radius difference, or delta R. Comparing Al and Ag, we find that the atomic radius of aluminum is slightly smaller than that of Ag. It means that aluminum has a slight advantage in fitting into the Zn structure. Next, we study electronegativity. Aluminum has an electronegativity of 1.5, while silver has an electronegativity of 1.9. In this case, the electronegativity comparison favors Al because both metals are relatively close, indicating they are more likely to form a solid solution with Zn. When it comes to crystal structure, both Al and Ag share the FCC structure. This gives us a tie in this criterion, meaning neither has an advantage over the other in terms of fitting into the crystal lattice of zinc. Finally, we consider the valences of the metals. Aluminum has a valence of +3, while silver has a valence of +1. Since a higher valence typically indicates a greater tendency to dissolve, this favors Al again. Based on these criteria, we conclude that aluminum is more soluble in zinc compared to silver. This prediction aligns with experimental observations, confirming the validity of the Hume-Rodary rules. By analyzing these factors, we can understand the behavior of different metals when mixed together. Now, let's talk about how we specify the components. In this slide, I'm gonna focus on linear defects, specifically dislocations, which are important for understanding how materials deform. Dislocations are one-dimensional defects where the arrangement of atoms is misaligned. They play a crucial role in the mechanical properties of materials, especially metals. First, we have the edge dislocations. This happens when there is an extra half plane of atoms inserted into the crystal structure. In this case, the Berger's vector, represented as B, is perpendicular to the dislocation line. You can imagine this as a kind of step in the crystal where one half of the plane is slightly out of line with the rest. Next, there is the screw dislocation. This type of dislocation looks like a spiral ramp created by shear deformation. Here, the Berger's vector B runs parallel to the dislocation line. It means that the misalignment happens in a more twist-like manner compared to the edge dislocation. The Berger's vector is a key because it quantifies the distortion of the lattice caused by the dislocation. It provides important information about the magnitude and direction of the defect, which in turn affects how the material behaves under stress. Knowing these dislocations helps us grasp how materials can be stronger or more ductile, depending on their structure and the presence of these defects. Well, let's look at edge dislocations in more detail, focusing on a 3D schematic that shows the dislocation line and the Berger's vector. In this image, you see the dislocation line, which represents the edge dislocation itself. This line is where the extra half plane of atoms is inserted into the crystal structure. Imagine a set of perfectly stacked layers of atoms, and then visualize one of those layers being pushed into the structure, creating an offset. This offset is the essence of the edge dislocation. Now let's talk about the Berger's vector, denoted as B. This vector indicates the magnitude and direction of the lattice distortion caused by that dislocation. In the schematic, the Berger's vector points in a direction that is perpendicular to the dislocation line, highlighting that it represents a step or shift in the atomic arrangement. The length of the Berger's vector is important because it tells us how much the atomic structure is distorted due to the presence of that dislocation. Typically, this vector is a measure of the lattice parameter, or the distance between two adjacent atoms in the crystal. To visualize this, you can see that the atoms above the dislocation line appear to be slightly pushed upward, while the atoms below remain in their original positions. This misalignment creates stress in the surrounding material, which is key to understanding how the material will respond to external forces. Edge dislocations are particularly important because they enable slip, the primary mechanism by which metals deform under stress. When an external force is applied, the movement of these dislocations allows the material to change shape without breaking, making metals more ductile. Well, in this slide, you can see screw dislocations, another key type of linear defects in crystals. In the left image, you see a 3D view of a screw dislocation. The dislocation line is the central line around which the atomic planes spiral. Unlike edge dislocations, where the displacement is perpendicular to the dislocation line, here the displacement is parallel to the dislocation line. The Berger's vector is also illustrated in this view. In a screw dislocations, the Berger vector is aligned with the dislocation line. It means that the direction of the atomic shift and the dislocation line itself run in the same direction. So this alignment creates a sort of ramp of atoms, allowing layers of atoms to screw around the dislocation line. In the right image, we have a top view of the screw dislocation. Here, we see how the spiral structure unfolds. So it shows how the atomic planes wrap around the dislocation line in a circular pattern, much like a screw turning into a material. Screw dislocations are significant because they play a vital role in the plastic deformation of materials. As stress is applied, these dislocations can move more easily than edge dislocations, contributing to the overall ductility and strength of the material. So, understanding screw dislocations is crucial for predicting how materials will behave under load and how we can manipulate their properties through processes like alloying and heat treatment. Now let's discuss the mixed dislocations. In right image, you can see a schematic representation of edge, screw, and mixed dislocations within a single crystal structure. So, how about edge dislocations? This type features an extra half plane of atoms inserted into the crystal. So, how about screw dislocation? This is characterized by a spiral arrangement of the crystal lattice around the dislocation line. And when it comes to mixed dislocation, this type combines elements from both edge and screw dislocations. Portions of the mixed dislocation behave like edge dislocation, while other segments exhibit screw dislocation characteristics. This combination can result in complex lattice distortions, contributing to various mechanical properties of materials. So, we see a top view of mixed dislocation in right image. This perspective helps visualize how the dislocation lines interact with the surrounding atomic planes. The mixed dislocation shows the transition between edge and screw dislocation features. So, knowing this dislocation type is essential in material science. Totally, dislocations play a critical role in how material responds to stress and deformation. Let's explore more. When we apply stress to a material, the dislocations within its structure begin to move. This movement is key to understanding how materials deform. Let's break this down. Movement under stress. When we apply stress, it can cause dislocations to shift. As these dislocations move, they create a slip in the material, which is a fundamental process in deformation. How about permanent deformation? The movement of dislocation leads to permanent or plastic deformation. It means that once the stress is removed, the material does not return to its original shape. Instead, it retains some of the changes that happened during the application of force. So, here we can see the difference between an unstressed or undeformed crystal and one that has undergone tensile elongation. I mean after plastic deformation. In the unstressed state, the crystal structure is regular and aligned. After tensile elongation, the movement of dislocation creates steps in the crystal structure. Each step corresponds to a dislocation that has moved to the surface of the crystal. These steps illustrate how dislocations facilitate the process of plastic deformation. So, knowing this concept is vital in material science as it helps us predict how materials will behave under different loading conditions. Well, let's shift to interfacial defects, which are important features in the microstructure of materials that can significantly influence their properties. So, I'm going to discuss two main types of interfacial defects: twin boundaries and stacking faults. The first one, twin boundaries, also known as twin planes. They are fascinating structures. They form when there is a mirror-like reflection of atom positions across a plane. Imagine one side of the twin plane being a mirror image of the other. This symmetry can affect the mechanical properties of the material, making it more ductile or strong, depending on how the twins are oriented and the material in question. The schematic shown here shows this concept of a twin plane or boundary, highlighting how the atomic arrangement is mirrored across it. Number 2, stacking faults. They happen when there is an error in the stacking sequence of atomic layers in a crystal structure. In the case of face-center cubic metals, the normal stacking sequence, as you know, is ABC, ABC. However, when a stacking fault happens, this sequence can be disrupted. For example, it might become ABC, AB, ABC. So, this change in the stacking sequence can affect the slip behavior in the crystal, influencing the material's strength and other properties. Finally, let's discuss the importance of microscopic examination in understanding materials, particularly focusing on grain size. You know, grain size is a crucial characteristic that can influence many properties of materials, such as strength or toughness. The size of grains in a material can vary significantly depending on the type of material and the conditions under which it was processed. In some materials, the grains can be quite large. For example, large single crystals of quartz, diamond, or silicon can have very visible grain structures. You can also see individual grains in aluminum, light posts, or garbage cans due to their larger grain sizes. On the other hand, in many materials, grain sizes can be quite small, often less than a millimeter. In these cases, a microscope is necessary to observe the individual grains. So, the size and arrangement of grains can significantly affect the mechanical properties of a material. For instance, smaller grains often lead to higher strength through a mechanism known as the Hall-Page relationship, which suggests that finer grained materials are typically stronger. Now, let's look at the optical microscopy, a fundamental technique used in material science. Optical microscopy uses light to magnify samples. It is effective for viewing microstructures at magnifications up to about 2000 times. This technique is commonly used for, seeing the surfaces and internal structure of materials, providing essential information about their properties. One critical step in preparing a sample for optical microscopy is polishing. Polishing removes surface features such as scratches and other imperfections, which is vital for obtaining clear images. A smooth surface enhances the quality of the observation. After polishing, etching is often performed. This process involves applying a chemical solution that alters the reflections of the surface. So, etching highlights the grain boundaries and changes the appearance of the surface based on the orientation of the grains, making it easier to analyze the microstructure. Optical microscopy can reveal the microstructure of materials such as brass alloy, which is a copper zinc alloy. The micrograph shows the different grains in the brass, allowing for analysis of grain size, shape, and orientation. Optical microscopy is a valuable tool for researchers and engineers, enabling them to gain insights into material properties and behaviors through visual examination. In this slide, let's focus on grain boundaries and their significance in microstructure analysis. As you know, grain boundaries are regions between individual grains in a material. These boundaries play a crucial role in the mechanical and physical properties of material. They are more susceptible to etching compared to the grains themselves, which is important for visualization. After the etching process, grain boundaries become visible as dark lines in the microscope images. So, this contrast enhances our ability to analyze and characterize the microstructure of the material. To quantify the grain size, we use the ASTM grain size number, which is given by this formula. N equals 2 to the power of g minus 1. Here, n represents the number of grains per square inch at 100 times magnification, and g is the grain size number. This method allows for standardization and comparison of grain sizes across different materials. So, in this photo, you can observe a polished surface under the microscope. The surface groove and dark lines indicate where the grain boundaries have been revealed through etching, providing insights into the material's structure. How about the role of polarized light in optical microscopy? So, polarized light is often employed in metallographic scopes to enhance contrast in microscopic images. So, this technique is particularly useful for revealing details that may not be visible under normal lighting conditions. So, the use of polarized light helps in distinguishing different materials and their phases based on how they interact with the light. This method is not limited to metals. It is also beneficial for observing transparent samples, such as polymers. By using polarized light, we can observe the internal structure and characteristics of these materials, including stress patterns and crystallinity. The increased contrast provided by polarized light allows for a more detailed analysis of microstructural features. This can lead to a better understanding of material properties and behavior. Now, I'm gonna explore electron microscopy and its advantages over optical microscopy. Let's start with resolution. The best resolution for optical microscope is around 0.1 micrometer, which is 100 nanometers. However, when we require higher resolution, we need to use shorter wavelength radiation. X-rays, while shorter in wavelengths than visible light, are difficult to focus, making them less effective for high-resolution imaging. But electron beams offer a significant advantage due to their much shorter wavelengths, potentially as short as 3 picometers, 0.003 nanometers. This allows for much finer resolution. With electron microscopy, magnifications of up to 1 million times are achievable, enabling us to see structures at the atomic level. Electron microscopy can achieve atomic resolution, which means we can visualize individual atoms within a material. This capability is invaluable for understanding material properties and behaviors on a fundamental level. In electron microscopes, electron beams are focused using magnetic lenses instead of glass lenses used in optical microscope. This focusing method allows for the precision required to achieve high magnifications and resolutions. In this slide, as an example, we observe dislocations as dark lines in the electron micrograph. When we look at a micrograph, these dark lines represent the presence of dislocations within the crystal structure of the material. Dislocations can be detected using electron microscopy because they disrupt the regular arrangement of atoms. creating a contrast that shows up as dark lines in the image. The visibility of these dislocations is crucial for understanding the material's properties. So let's look at another example. Catalysts are crucial in many chemical processes, particularly in industrial applications and environmental chemistry. So let's explore the role of catalysts and how surface defects are involved in catalytic reactions. A catalyst is a substance that accelerates the rate of a chemical reaction without being consumed in the process. It means that once the reaction is complete, the catalyst can be recovered and reused. They are essential in various applications, from speeding up reactions in chemical manufacturing to reducing harmful emissions in vehicles. So, catalytic reactions often take place at surface defect sites. These defects can include, ledges, steps, terraces, and additives on the catalyst surface. Surface defects provide unique sites where reactants can adsorb, facilitating the reaction to happen more effectively. In the image from a transmission electron microscope, we see single crystals of Ce 0.5, Zr 0.5, O2 ceramics, commonly used in automotive catalytic converters. The features displayed here include ledges, steps, trusses, and additives. Each of these structures contributes to increasing the active surface area of the catalyst, which enhances its efficiency. Next, let's discuss scanning tunneling microscopy, or STM, which is an exceptional technique for imaging surfaces at the atomic level. STM uses a microprobe that tapers to a single atom at its tip to image surface atoms. This unique design allows the probe to get extremely close to the surface, enabling it to detect individual atoms. One of the remarkable features of STM is the ability to rearrange surface atoms. By pushing the probe tip, we can move atoms into desired positions. This capability is particularly useful in nanotechnology and material science for fabricating nanoscale structures. It is done. If you enjoyed this video, please like, share, and subscribe for more engaging content in material science and engineering. Your support helps me continue exploring these important topics together. See ya.